In this video, we'll take a brief tour of the Properties Library. Before we begin, let's consider the context and use cases for which properties are intended, but without actually using properties. The use case is a particular subset of concept-driven design and involves three parties: a user's application, a library providing algorithms, data structures, and other generic facilities, some kind of infrastructure, which is also a library, but which is providing a lower-level facility on which the generic library is built. The interaction between these three parties is defined in terms of what we'll refer to as a concept. In this context, this is some kind of interface to support compile-time polymorphism and is typically specified as a concept or type requirements. Importantly, the concept defines not just the syntactic interface, but also implies a set of allowable behaviors and semantics, which can potentially be very broad. The infrastructure provides a concrete implementation of the concept. The library consumes the concept. The user is responsible for obtaining the concrete implementation from the infrastructure and supplying it to the library. This establishes the link between those parties. As a concrete example, let's consider a hypothetical allocator concept. A key characteristic of our context is that the infrastructure is itself divided into two parts. The first is a conceptually long-lived component. In the case of an allocator, this represents the underlying memory resource, such as a heap. Here is a sketch of what this long-lived resource might look like. As you can see, it is a non-copyable class, and it provides a function to return the second part of the infrastructure, which is a concrete implementation of the concept. This implementation is typically lightweight, has reference semantics, and will be copyable or movable. Here's a sketch of our concrete allocator implementation. As you can see, it's copy constructible and provides the allocate and deallocate functions as required by the concept. Next, let's take a look at the library, which in this case is providing an algorithm. Our algorithm accepts the concept object by using compile-time polymorphism, here as a template parameter, or runtime polymorphism, such as a type erased wrapper. The role of the user is to simply create the long-lived resource and from it obtain the concrete implementation of the concept. This is then passed to the algorithm. This hypothetical allocator is of course just one example of this kind of design. Other examples include using allocators with containers and executors, obviously, as that was the use case from which properties evolved. Here, the concrete executor is passed to what we in the executor space have been calling a control structure. Control structures include algorithms, asynchronous operations, event notification channels, and more. And finally, another example to consider is the iterator concept and the way it connects long-lived containers with algorithms. The Properties Library is a small facility that has four key elements: the customization point objects named query, require, prefer, require concept. Let's start with query. We'll continue using our hypothetical allocator example. Let's start by taking a look at the algorithm. Our algorithm takes the allocator as a parameter. Let's assume that our algorithm has a generic implementation, but also lends itself to an optimized implementation if the allocator is guaranteed to supply it with page-aligned allocations. The algorithm might be structured something like this. To support this with the Properties Library, we begin by defining a new property which we will call alignment. As properties are identified by their type, we begin by defining a new type called alignment. Alignment has a member template variable isApplicable property v to ensure that it can only be used with allocators. Next, we add support for our new property to our infrastructure. To do this, we add a new member function called query, which returns the current value associated with the alignment property. The property object is passed to query as an argument so that overload resolution is used to select the right query function. We then change our algorithm to call the standard query customization point for the alignment property. This returns the current property value associated with our allocator. However, this code will only compile if the concrete allocator implementation supports the property. To allow our algorithm to work with all allocators, even those that don't support the alignment property, we can use the standard canQuery trait to determine whether the query is well formed. Now our algorithm will compile even if the property is not supported. However, for certain properties, it may make sense to provide a fallback implementation of the query. This means that the property can always be queried even when it is not natively supported by a concrete allocator. We do this by extending our alignment property to add the fallback implementation as a free function. The standard query customization point will try to use the allocator's query member function first, and if it's missing, will fall back to the free function here. Now we can clean up our algorithm so that it unconditionally calls standard query. Alignment isn't going to be the only property that makes sense for allocators. You might imagine a number of other properties that can be used to describe allocator behavior. One way of thinking about this is to imagine the allocator concept as defining a set of possible behaviors. Algorithms can still operate generically on this concept without being aware of the object's properties, as long as they assume that the behavior can be anywhere in this set. However, a concrete allocator object can also be thought of as having a bag of properties. Each property describes a subset of the possible allocator behaviors, such as alignment and locality. By querying the properties, we can establish where in the set our particular concrete object lies. However, even if an algorithm is aware of properties, it only needs to query the properties it cares about. For comparison, consider some existing practice where both the infrastructure and library are implemented by the same vendor. In this case, the algorithm might test for vendor-specific concrete types to determine whether an optimization is possible. We can imagine that this vendor-specific concrete type represents a specific point within the set of behaviors. Properties allow us to test for this without tying us to a specific type. To complete the picture for query, we should also point out that certain properties queries can be performed wholly at compile time. This is achieved by giving the property a static query v template data member. This allows the query to be used for compile time metaprogramming. Next, let's take a look at require. We'll continue using our hypothetical allocator example. However, this time our infrastructure's long-lived component, the memory resource, is capable of supporting a range of different behaviors within the allocator concept. Now, when we write our algorithm, we want to know whether the supplied allocator can be asked to support page-aligned allocation. If it can, we'll use that to enable our optimized implementation. To do this, we add an isRequireable static member to our alignment property. This enables our property to be used with the standard require customization point. To support this in our infrastructure, we add a new require member function to our concrete allocator implementation. As with the query, this uses the property type to distinguish overloads. In this case, the property also carries the value requested by the user. The require function returns a new allocator object that is identical to the original except for the change in the value of the alignment property. We can then call standard require to obtain the new allocator with the requested property. As with query, this will only compile if the allocator supports the property, so we can use the canRequire trait to ensure our algorithm compiles either way. Or we can do as we did for query and provide a fallback implementation as a free function. In this case, our fallback will return an adapter around our allocator that over-allocates memory and aligns to the requested boundary. Whether this is worth doing in practice very much depends on the property. For properties that have a fallback like this, the algorithm can call standard require unconditionally. When we call require, we are exchanging our allocator object and its bag of properties for another allocator object with an updated bag of properties. If we think of our universe of allocator concept behaviors represented as a set, then when we call require to obtain our updated allocator object, we are returned an allocator object that we know to reside within a particular subset. We can use this information to optimize our algorithm. However, the updated allocator object is still within the set of conforming allocator behaviors as implied by the concept, and so can still be used generically as an allocator. Prefer. Once again, we'll use our allocator example. With our infrastructure component supporting many different behaviors. However, this time, our algorithm has a single generic implementation that just happens to be significantly faster when given page-aligned memory. This is a use case for prefer. To make our property usable with prefer, we add the isPreferable static member. Then our algorithm can use prefer to obtain an allocator that may support page alignment. If the underlying infrastructure supports the requested property, then a new allocator with the updated property is obtained. However, unlike require, if the property is not supported, then the same allocator is returned. Require concept. Now let's change our example so that we have allocators that are typed on the object being allocated. And our algorithm may need to allocate different types of object at different stages. In this scenario, our underlying infrastructure is accessible through multiple concepts or interfaces like allocator of int and allocator of my class. For example, if we create a property called allocator of, to make it work with require concept, it must provide the static member is requirable concept. It should also provide a static query v template member to determine whether a particular type adheres to the concept at compile time. As we did with query and require, we add a member function require concept to our concrete allocator implementation. Our algorithm can now use require concept to obtain a new allocator conforming to the requested concept. For this reason, properties that are used with require concept are called concept enforcing properties. On the other hand, properties used with require are called concept preserving. By calling require concept, our algorithm obtains a new concrete allocator implementation that still refers to the same underlying long-lived component. Require concept may also be used to navigate between different concepts that expose an infrastructure component's behavior in different ways. For example, consider a hypothetical enriched allocator concept that supports in-place growth of allocated memory. Our algorithm then detects whether this enriched interface is available, and if so, uses it to provide an optimized implementation. Related work. You may have noticed that properties seem quite similar to traits. Properties are, in fact, traits. However, properties are traits with a well-defined vocabulary that allows them to be used generically. This is important in use cases like executors, where adapters like the polymorphic wrapper need to store and manipulate properties in a generic context. Early attempts at unifying executors explored the use of concept hierarchies to classify the possible behaviors. However, this turned out to be extremely unwieldy, as the behaviors typically represented cross-cutting concerns. The hierarchy depended on an arbitrary ordering of the importance of the behaviors, and in any case would have required a combinatorial explosion of concepts to cover the entire set of behavior. The problems being addressed by properties are not particularly new. The extension interface design pattern allows multiple interfaces to be exported by a component to prevent bloating of interfaces and breaking of client code when developers extend or modify the functionality of the component. The pattern is found in COM and Corba components. Properties exhibit many of the characteristics of this design pattern, except that in C++ we can leverage the type system and compile time polymorphism, rather than having to inefficiently negotiate supported behaviors at runtime. And finally, you can find an implementation of the properties library at the website shown here. Thank you for watching.